issues. I just got some stuff from Cotton this morning, which I'm supposed to get off the Wileys by return, but it's not going to be today.
And how did you come to write the book with Cotton?
Well, he was my first graduate student at Harvard.
And the idea for this was?
Well, it was actually his idea because, I mean, he took the first course in inorganic chemistry, first course I'd ever given in my life. I mean, that was one of the things that I had to give at Harvard when I first went there. And then he decided to work with me. He'd come to actually work with George Kistiakowski, but he decided after he'd taken my course to work on inorganic chemistry. So he's my first graduate student, and after he'd finished and was going off to MIT, he said, why didn't I write up some of my lectures, you know, as a textbook, because at that time it wasn't really a good textbook. So I said, okay, I'll do it if you come in. So when I came back here in January 1956, I mean, that's when he was at MIT, and then he came over that summer, and in my father-in-law's office. My father-in-law was the director of the pharmaceutical high school in Copenhagen, and we sat in his office and sort of drafted out his textbook, and we started writing, and 5 years later we had the first edition, and this is the 5th edition.
And how much do you think that contributed to recognizing the work you did on homogeneous catalysis?
Oh, that was nothing to do with that. That was years before that. I mean, this was 1960, the first edition. I mean, what that first edition did, I've done more outside, is revolutionized the teaching of inorganic chemistry. I mean, that was probably the biggest revolution in inorganic chemistry that will be this century, that textbook.
And does that give you equal satisfaction to the research work? Or?
It's made it possible for me to live in London. That's the only thing I can say to you. I mean, if it hadn't been for that, I'd have been on the uppers.
And what led you to the work in complexes that eventually became known as Wilkinson's catalyst?
Well, it actually started with some work I actually did myself. It was actually the last piece of work I published under my own name, which was the idea that, see, I discovered when I was working in Copenhagen, I discovered a well-known compound now, which was cyclopentadienyl rhenium hydride. And this was the first compound in which the spectroscopic characteristics for a metal hydride were able to be determined. I mean, it turned out this used to have, or it still has a band at 2,000 wave numbers, but this was just the time nuclear magnetic resonance was being brought in, and we didn't have an NMR machine at Harvard. And I knew Earl Mutites, who was one of the graduate students at Harvard, and he was at DuPont. And I rang him up and said, look, I've got this interesting new compound, can you run the NMR spectrum? So they ran the NMR spectrum, and they saw the peaks for these cyclopentadienyls down here. They couldn't find anything else. And I said, look, run it, you know, as far as you've ever run it. And this was quite remarkable. They found this hydride peak way out at the high field line in a previously quite unrecognized region. So that got me off onto hydrides, and then many other hydrides were made subsequently, but they all had either organometallic ligands or carbonyls or pi bonding ligands. And it occurred to me that it should be possible to make metal hydrides with non-pi bonding ligands, that's say amines, and I picked one of the so-called substitution inert rhodium species, which was that one, the dichloride, this ethylene rhodium dichloride, and I just treated it with borohydride, and I was able to characterize those hydritic species. Now this then led me into looking at other amine hydrides, and we did quite a bit of work on substitutions, and found that alcohols, in fact it was an old observation that, by Delapine in France, that alcohols and hydride, well not so much really alcohols, but we able to show that hydride sources were able to speed up substitution reactions of that sort. And we finally got on to a rhodium system, which was rhodium trichloride plus pyridine, and found that that reaction to give rhodium trichloride pyridine, and then to give rhodium pyridine 4 times Cl2 cation. This was speeded up by hydride sources, and I said to Bob Gillard and John Osborne, who were my students at the time, why don't you try molecular hydrogen? So we tried molecular hydrogen as a hydride source, and lo and behold, molecular hydrogen catalyzed this reaction. So then I'd always sort of been vaguely interested in hydrogenation, so I said, well look, why don't you put some olefin into this system and see if it'll catalyze the hydrogenation of olefin, in other words to catch any intermediate hydrides here. So we did indeed put some hexene into this system, and indeed hydrogenation to hexane. But the system was actually rather labile in the sense that it readily deposited rhodium metal. In other words, it hydrogenated the rhodium chloride pyridine system, hydrogenated hexene quite nicely, but the rhodium complexes were unstable, and you got black rhodium coming out. So then the next thing was to say, well, okay, we'll try something which stabilizes the metal to reduction, the complex to reduction down to metal. So what do we do next? Obvious thing to do is to replace pyridine by triphenylphosphine, which was, and this particular compound was a compound rhodium trichloride, triphenylphosphine 3 times, had been claimed by Luigi Venanzi. So we tried that system, and that indeed also acted as a catalyst. But we had trouble repeating Venanzi's prep. And I remember saying to Fred Jardine, who was a student who was doing this, why don't you chuck in a large excess of triphenylphosphine? Instead of using the stoichiometric amount of phosphine here, as Venanzi did to get this, I said, why don't you use a large excess? And if we use a large excess, what we got out of that was a nice red crystalline. Instead of being rhodium-3, it was rhodium-1, and that was what now people known as Wilkinson's compound. So that's how we actually discovered it. It was the sort of over a period of years from doing the original hydride substitution on this rhodium bisethylene diamine complex, through the hydride catalyzed substitution reactions of rhodium, to the pyridine rhodium system, then to the pyridine rhodium 3 system, and then accidentally we made that rhodium 1 species. So that's how Wilkinson's catalyst, so-called, was discovered.
And then after you observed that it hydrogenated?
Well, I mean, we tried this one then by itself, and of course this went like a bomb. You see, you could actually see the hydrogen, 1 atmosphere, you could see the hydrogen manometer just went up like that.
And then you decided to work in other areas after this, rather than catalysis?
Well, I mean, the only other thing really in catalysis I did subsequently, apart from doing the catalytic system with this, then we went on and made analogues. I mean, the one that we subsequently made was a ruthenium hydride chloride for phosphines, which again was an extremely rapid hydrogenation catalyst system. But then doing the reactions of that rhodium chloride trisphosphine, we showed quite easily that this stuff really reacts quite easily with carbon monoxide and gives rhodium chlorocarbonyl. So then I had the idea that we might as well just have a look at this rhodium system for doing hydroformylation, because the hydroformylation reaction was discovered in Germany by Röhrlen in about 1936 or 7. I think the first commercial plants were probably put up after the war, at least in the States. I think they had an operating plant in Germany during the war. That was carbon monoxide, hydrogen plus olefins to give alcohols. But the problem with that was always that they got a mixture of straight to branch chain alcohols out of it, and there had been quite a bit of work, people trying to improve this. So anyway, we tried this rhodium system, and that did indeed work quite nicely. But eventually it wasn't the chloride that we found was the effective catalyst. It was actually the hydridyl species, rhodium hydridocarbonyl tristriphenylphosphine. And on working with that, we found that if you actually load the system up with excess triphenylphosphine, that you get very highly selective hydroformylation from alk-1-ene to give the straight chain aldehyde. And it was unique in the sense that here was a system which would actually give you pure, essentially pure, or 98% of the straight chain aldehyde from the olefin. So in other words, you'd added the hydrogen and the formyl group as hydroformylation. You'd added them anti-Markovnikov to the double bond. And there was some similar work done by Union Carbide in the States by my old friend Rod Pruitt. And what this led to eventually was commercial development of this rhodium excess phosphine system as a tripartite arrangement with Johnson Matthews here, who had my patents on this stuff, with Davy Powergas, the English plant constructors and chemical engineers who'd improve the sort of recycle for the gas recycle, and Union Carbide, and so that has been a very successful commercial process, which is now operated by about 8 or 9 companies all over the world. So that was really my rhodium catalysis, one on one side the Wilkinson's catalyst, and stemming from that they were going into hydroformylation. And well, both things have in effect been commercial. I mean, I haven't probably made as much money on the on the patents on Wilkinson's catalyst as I should, because I think a lot of pharmaceutical companies have just picked that up and applied it to their own systems, and you know, you can't stop people doing that, really.
Now, how were you aware of the patent system and would take out a patent on this? Well,
I wasn't quite as smart as I should have been. I was a bit naive about patents in those days, but at least I had enough sense to patent, which in fact I did myself with the rhodium fluoride system. Then I persuaded Johnson Matthys, from whom I was borrowing the rhodium, to sort of take the patents out on the other thing. So really, I mean, Johnson Matthys helped me, you know, take out the patents and so on, and that put them into a position where they were able to go in with, certainly on hydroformylation, with Davy power gas initially, and then subsequently union carbide.
Well, after the prize, people say there's about a 5-year period where one has to work hard, having won that, and get away from science. Yes.
Oh, it made absolutely no difference to me at all. I mean, I just kept on doing exactly the same thing I was doing before, which was running a few students, and I mean, we've done odd little bits on catalysis since, but I mean, effectively, I haven't really. I mean, I was never really a catalysis chemist in that sense. I mean, I was an organometallic chemist. I was a coordination chemist. I was just doing as best I could, as I'm still doing, new chemistry. If some of the things happen to be catalytically useful, okay, but I mean, I never deliberately, you might say, set out to work on catalysis.
What would you say is your the thing that gave you most pride so far in what you've done?
Well, it's difficult to say. There's a lot of things I'm quite pleased with, but I suppose the original thought of the sandwich compounds, which was when I was at Harvard. The second thing I'm always quite pleased with, because I was 10 years before anybody else, was the recognition of fluxional molecules. You know, these things where things are rotating, which was work that I did at Harvard on this cyclopentadienyl iron dicarbonyl, and we made what was the sigma compound, which you can write that way. And this was, I think, the first organometallic compound that was ever measured, apart from the rhenium one I mentioned before, which was measured at DuPont. This was the first that was done on our first NMR machine at Harvard, and that's where one saw this sharp band for this cyclopentadienyl ring here, and then one saw a very broad peak, and that was this other ring here, and I worried about this for a long time until I recognized it was a matter of time scale on which you have the spectra. Infrared spectra, the time scale is sort of 10 to the minus 10 seconds, whereas NMR is sort of 10 to the minus 4, 10 to the minus 5 seconds. And I was sitting at my desk, which happened to be a well-known desk because it was the desk that Theodore W. Richards used when he was at Harvard. And because he got the Nobel Prize for his work on atomic weights. And I was sitting with my feet up at that desk. And of course, I'd been a photographer, I suppose, when I was about 15. And it suddenly struck me that if you take a photograph of a moving wheel at, say, 500th of a second, you'll stop it. If you take it with a 1 second exposure, you just see a blur. That's exactly what this was. I mean, the difference in time scale on the infrared spectrum, you know, and the NMR spectrum, the order of magnitudes of difference in the time in which you were looking at a molecule. You could stop this unique hydrogen here by infrared, but you couldn't stop it because this thing was doing a 1-2 shift, and that ring was actually just going around. And that was really the first discovery of a fluxional molecule, so I was quite pleased with that. And it was 10 years before another one was discovered.
But NMR was rather new at that time. How did you become interested in NMR?
Well, I only became interested in NMR because I had then a specific problem, and then Harvard got the first NMR machine that Varian ever produced, and then I started running some of my things on NMR. I was particularly interested in the metal hydrides, And, you know, this one was, we just started running it through NMR spectra, and this was, in fact, the first one we ran, and it showed up this quite remarkable phenomenon. So, quite pleased with that. Quite pleased with Wilkinson's catalyst. Quite pleased with the first really stable transitional metal alkyls in high oxidation states, of which perhaps the most amusing one, for which I won a bet from Henry Talbot that it couldn't be made, was hexamethyl tungsten. Hexamethyl tungsten. Nobody in the right mind, I think, would have predicted that hexamethyl tungsten could ever be made, or indeed would be stable. And I remember betting Henry Talbot, this was when I was consulting for Hercules, once that, you know, that thing, if you could only find a way of making it, it would be stable. And we did indeed try, and more or less accidentally, we found a way of, well, we were trying to make it, but I think if we hadn't had an accident in the way that we were doing it, we might not have spotted it. And that was because when you treat WCl6 with, say, methyl lithium, you get reduced species, which we could never characterize, and it was only by having some adventitious oxygen in there that we could oxidize these reduced species up to hexamethyl tungsten. So, and that was because a student was not degassing his petrol properly. I mean, if he degassed his petrol properly, we'd probably have never spotted this stuff. So that was a lucky break. So, I mean, those are some of the things that sort of, you know, kept me amused. And there are other things I've done, like making molybdenum diacetate, which is the first MO2 acetate 4 times, which has been a very fashionable molecule ever since, and people have done hundreds of papers. You know, it's one of these things that opened up hundreds and hundreds of publications. So you look back and say, you know, there are some molecules that you're quite pleased to have made.
Do you consider yourself more of an experimentalist or a theoretician or both?
Oh, experimentalist. I mean, I don't really care very much about the theory. And I mean, when I was at Harvard, there was one of my friends who was an English student originally of Coulson's, and it was becoming fashionable to talk about theory and ammo stuff and all that sort of stuff at that time. And I was sort of rather impressed by this sort of theory. But I remember Bill Moffat saying that, you know, don't worry about the theory, Geoff, because A, in 5 years' time the theory will be obsolete, but your compounds will be good still, you see. And then I've had other experiences with a friend of mine in Copenhagen where I told him, because of the experimental work we've done, at certain sandwiches, that rhenium one, for example, had to be bent, because we'd actually made a series of cyclopentadienyl rhenium hydride, cyclopentadienyl molybdenum dihydride, and cyclopentadienyl tantalum trihydride. And we got the NMR spectra of these things, and also we showed that this could be protonated by acids. This one could be protonated by acids. So we had to postulate a lone pair there, 2 lone pairs here, and the only way you could do this is by bending the rings. So I told Carl Bauhausen in Copenhagen what we'd done. I said, look, we come to the conclusion that these things have to be bent. There are lone pairs here. In the tantalum trihydride, there's no lone pairs. And then, blow me, he didn't believe it to begin with. So I said, well, look, why don't you go away and think about it? Then he goes away and thinks about it, and about 6 months later, publishes a paper predicting. Yeah, he knew the answer to begin with. And I'm afraid that's my attitude to theory. The other thing, I mean, at Harvard, I remember once saying to Bill Moffat, look, cyclopentadienyl anion minus 6 pi electrons. Benzene, 6 pi electrons. Another 6 pi electrons. I said cyclopentadienyl can bind to a metal. How about benzene? And he went away and thought about it and came back and said, oh no, all the symmetries and the energy levels, they're all wrong. You know, no way. But, I mean, you know, he was a theoretical chemist. I believed him. I should have done the experiment. Because, in fact, the benzene compounds have been made but not recognized. This was old Heinz polyphenol chromium compounds from 1922 and 1923. They were in the literature. I knew about it. That's what I thought, you know. He said, oh no, it must be something else. And then, damn me, Harold Zeiss at Yale came up because Ansager had that idea as well. And Ernst Otto Fischer in Germany did the same thing. And I could have done the damned experiment about 2 years before. I mean, I wouldn't have done what they would have done, but all I would have done was to, which is, I kicked myself for not having done this. I should have technically say molybdenum carbonyl plus benzene. And if I'd done that, I would have got benzene molybdenum tricarbonyl. But I never did the experiment. So ever since then, I've taken not the slightest bit of notice of theory. And it's very interesting, in this 5th edition of this well-known textbook, there's hardly any theory left. I mean, even my colleague F. Albert Cotton, who's certainly more theoretically orientated than I am, I mean, we've decided, you know, facts and experiments are more important than theory. So, no, I'm an experimentalist and an empiricist. I mean, you know, if I get an idea, I just say, all right, well, let me try it out. I mean, some of them work and some of them don't. But if you come up with 51% of your experiments working, you're winning, you know.
Well, you sound like you found it difficult to give up the hands-on experimental work. Is that a...
Oh, yeah, yeah. I mean, I'd never do that. I mean, I have to retire at the end of this year, but as soon as I get this book out of the way, I'm just preparing myself to start doing some more experimental work, so I think I'll keep on going. And I was very impressed when I was in Berkeley 6 or 7 years ago. I was there just about 2 or 3 days after, what's his name, that famous chemist who died at the age of 103. You know, he trained the American Olympics in 1935.
Noise?
No, not Louis. Oh, my mind's going. Anyway, the point was that he had just been turned down by the National Science Foundation at the age of 95. Not on the grounds that the science was wrong, but on the grounds that they didn't think he would live to complete the program. So, no, I you know, keep going, do experiments. I mean, it's the only thing you can do. I mean.
Well, why do you think England has been an area where inorganic chemistry seems to thrive over a long period of time?
Well, it didn't thrive over a long period of time, I think. I mean, it was marginally better than the United States, but my chair here was the only established chair of inorganic chemistry in the entire country when I came back from Harvard in 1956. So
you started a new trend in...
Well, there were 1 or 2 other people. I mean, MLS was a personal professor in Cambridge, and I worked with MLS in part, although I was officially my supervisor. HVA Briscoe was officially my supervisor. And there were 2 or 3 other people scattered around. There was P.L. Robinson up in Durham, and Freddie Fairbrother in Manchester. But there was hardly any more emphasis on inorganic chemistry in this country than there was in the States. And in the States, you could count the places, and, you know, there was John Baylor and, well, I mean, There were 2 or 3 people at MIT, all shown young. There was KD doing fluorine chemistry. You know, there were a handful of people, and inorganic chemistry was hardly a subject in most universities in the United States at that time. And you know, this is only 35 years ago. So there's been a dramatic change ever since. I mean, both in this country and in the States. And I think maybe, you know, our book helped this along. But I think it was a time when people were beginning to realize, largely because of the importance of inorganic chemistry in the atomic energy projects during the war, which is largely all inorganic chemistry when you come right down to it, that it was, you know, an essential discipline, and it had been neglected, except in Germany. A lot of inorganic chemistry in Germany before the war. I think if you pick up the first edition of Amelaeus and Anderson's textbook, I mean, they essentially apologized for all the German references and said this is a reflection of the, you know, the lack of inorganic chemistry in the English-speaking countries. I think there was almost as much proportionately in Australia. You know, Australia had quite a sizable sort of, compared to the total numbers, the Australian inorganic chemistry, of which Ronald S. Nyholt was a product. I mean, Frankie Dwyer and people like that, I mean, they were quite strong in Australia. But, you know, elsewhere in the States, Canada and this country, very few and far between.
I don't know whether you realise today is Commemoration Day at Imperial College, and that is the time when degrees, diplomas, etc. are handed out to the graduating classes. You may have heard the bells, did you? It's the Queen's Tower. It's all that's left of the old Imperial Institute. Are you actually recording now? Oh, you are. Oh, splendid. See, Imperial College was, the original foundation was the Royal College of Chemistry. That was 1845. And the Prince Consort had a big hand in its initiation. He was the consort of Queen Victoria, and he was German, and in that century, the last century, the German technical high school system began, and the Royal College of Chemistry was a sort of